This video will focus on Section 2 of Chapter 5. We'll discuss the binomial probability distribution, learn what it is, and how to apply it. The binomial probability distribution. So what are the characteristics of this? The binomial probability distribution we still consider having experimental outcomes, or trials. Each trial has only two possible outcomes. Notice two binomial. So there are two possible outcomes. We talk about those as success or failure. Success meaning finding the thing that we're looking for, failure meaning we didn't find the thing that we were looking for. There is a fixed number of trials, that's n. N is going to be finite or countable. Each of those trials are identical. The trials in the experiment are independent of each other. So one trial does not impact the probability of the second trial. The probability of success, finding the thing we're looking for, remains constant from trial to trial because of this independence. So the probability of the first item being successful is going to be P. The probability of the second item being successful is also going to be P. If P represents the probability of success, then 1 minus P, that's our complement rule, represents the probability of failure. Q is how we represent the probability of failure. So a few examples of where we might apply the binomial probability distribution. A manufacturing plant labels items as either defective or acceptable. The firm bidding for a contract will either get the contract or not. A market research firm has survey responses that say yes I will or no I will not buy your product. New applicants either accept or reject the job offer. To be able to calculate these probabilities, we need to be able to compute something called the combination. This combination counts for us the number of ways that you can choose X objects from our sample of N objects. The notation here on the left is read N choose X. To calculate that, we're going to do N factorial divided by X factorial times N minus X factorial. If you haven't seen factorial before, we define that for you down here. N factorial is really just N times N minus 1 times N minus 2 times till we get down to 2 times 1. So if this were 10 factorial, this would be 10 times 9 times 8 times 7 times 6 and so on times 2 times 1. X factorial is the same idea. Whatever x is times the next number down and so on till we get times 1. We do have a definition here with factorials. 0 factorial is considered 1. This is just by definition. So we take that idea as given. So this combination formula will calculate for us the number of ways that we're going to find X successes in our N trials when order doesn't matter. So here's an example. 35% of all voters support Proposition A. If a random sample of 10 voters is polled, what is the probability that exactly 3 of them support the proposition? We are not quite ready to calculate the probability yet, but we can count up the number of ways that we can pick 3 voters from the sample of 10 using our combinations formula. So we'll read this as combination 10 choose 3. 10 factorial divided by 3 factorial times 10 minus 3 factorial. So that's really 10 factorial divided by 3 factorial, 7 factorial. I use this notation because when I do this by hand, this is what I do. I break this top one down, 10 times 9 times 8 times 7 factorial, which is still the 7, 6, 5, 4, 3, 2, 1, divided by 3 times 2 times 1, times, I still have that 7 factorial. These two guys just divide out. And then I can focus on what I have remaining over here. So 10 times 9 times 8 divided by 3 times 2, that actually is 120. There are 120 ways that we can pick exactly 3 voters from the 10 voters. To calculate the probability, we need to do a little bit more. So this piece here that you see in this formula, that's really just the combination N choose X thing that we just calculated on the last page. So for our voters example, we already know that that's going to be 120. This piece here is that probability of success, and raising it to the X power is actually going to mean P times itself, however many successes we have. Q is our probability of failure, and we raise that to the n minus x, or our number of failures. So if we had 3 successes, we'd have that probability of success times itself a total of 3 times, times the probability of failure times itself a total of 7 times. So p to the 3rd power, q to the 7th power for our voting example. So let's actually plug that in and work it out. So this is the same setup we had just a moment ago. Exactly 3 voters out of 10 support the proposition when we know only 35% of all voters support the proposition. The notation we would use here is the probability of x equal to 3, and we're going to plug in all the pieces we just saw from that last slide. So 10 factorial over 3 factorial, 7 factorial. This 0.35 is our probability of success, the probability of finding somebody that supports proposition A. If we want to talk about finding 3 people that support proposition A, then we'd have 0.35 times 0.35 times 0.35, or in shorthand notation, 0.35 to the 3rd power. If 3 people support the proposition, that means 7 people do not support the proposition. So our probability of success is 35%. That means our probability of failure is 65%. So 0.65 for each of the individuals in our sample that don't support the proposition. 0.65 times 0.65 times 0.65 7 times, because we're assuming 3 support and 7 do not support the proposition. If we simplify this, we get 0.2522, or there's a 25% chance that exactly 3 of the 10 voters will support proposition A. Just like other distributions we've looked at, we can calculate the mean of the distribution. This is the population mean. It really is an expected value. So how many successes do we expect? We expect n times p successes. The variance and the standard deviation are calculated as follows. The variance, so notice sigma squared, is equal to n times p times q. The standard deviation is just the square root of that n times p times q. So let's start to see that mean and standard deviation in application here, and note some other characteristics of the binomial probability distribution at the same time. The shape of the binomial probability distribution depends both on the value of p and on the value of n. So you notice if we have n equals 5 successes, and the probability of success is 0.5, our distribution will be centered at 2.5. If there are 5 observations and we expect half of them to be successes, then we expect about 2.5 successes, and the distribution will be centered around that probability. N equals 5. We get only a few bars across 0 to 5, and we see a pretty good probability at each of those possible number of successes. As we move across the slide here, the number of trials goes up, but the probability is held constant. So if n equals 10 trials, and we expect about half of them to be successes, we would expect the center of the distribution to be at 5, and we'd expect to be able to have 0 to 10 possible successes in our 10 trials. Notice the probability of being at 0 and 10 is much smaller here than it is down here being at 0 and 5, because we're spreading this over a greater number of successes. If we increase our sample size to 50, and we still expect a 50% chance of success, we would expect about 25 successes. So that's the center of our distribution. And note the shape of that distribution. We get lots more bars because we have more options due to those 50 trials. And the probabilities of being way far away from 25 are small relative to what we see in these other distributions. This slide has us changing our probabilities instead of changing our sample size. The number of trials in both of these binomial probability distributions is 5, but here the probability of success is only 10%. If the probability of success is only 10%, in 5 trials we have an expected value of only half a success. Now we really can't have half a success, but that's the expected number of successes in 5 trials when our probability is only 10%. We can calculate the standard deviation for this. So the standard deviation is the square root of n times p times q. So the square root of 5 times our probability of success, which is 0.1, times our probability of failure, which is 1 minus 0.1 or 0.9. If we simplify that, we see the spread in this distribution is 0.6708. Those numbers are lumped pretty closely together down near this number of successes being 0. Our mean in this second example, with a probability of success being 0.5, is 2.5 successes. 5 is our sample size, or our number of trials. We expect about half of those to be successes, so we would expect 2.5 successes. Notice the distribution is centered at 2.5 and spread out evenly around that. Our standard deviation is the square root of 5 times 0.5, because that's the probability of success, times 1 minus 0.5, our probability of failure. Our spread in our data here is larger, 1.118. One more example of probability. Suppose we have that problem we were looking at before. 35% of all voters support Proposition A. We're going to take a sample of 10 voters, but instead of looking at exactly 3, suppose we're interested in the probability of 3 or fewer of those voters supporting that proposition. So we want to find the probability that X is less than or equal to 3, given those same 10 trials and the probability of success being 0.35. To do less than or equal to 3, we actually have to add up the probability that we'd get exactly 3 voters, 2 voters, 1 voter, or no voters supporting Proposition A. So we'd actually have to calculate the individual probability of exactly 3. Well, we did that before and we got 0.252. The probability of exactly 2 voters supporting the proposition, that happens to be 0.176. The probability of 1 voter is 0.072, and the probability of no voters supporting the proposition is 0.013. If we add those all up, we get that there's a 51% chance that 3 or fewer voters will support the Proposition A. Well, that makes pretty good sense, because in our population, 35% of the voters support Proposition A.